Okay, so let's continue now. Let's see. Right. So we are now going to see the tangent bundle of a smooth manifold. So first of all, I would like to recall and do all of the concepts. Yeah, from the point of view of sets, nothing continuous or smooth so far. So we have a manifold M, and then we have a new set, Tn, which is the set of all the points in the manifold and vectors in the tangent plane to P. Right? So you can think about it also this way. So it's not any point and any vector. It has to be a vector that belongs to the tangent space at that point. So we have a natural projection map to the manifold M. We will usually call it pi. So from the tangent bundle to the manifold. And it will just give me the point or base point. Now, what is the preimage of a point in M?
Like it's tangent space.
Right.
But P.
So it is, so that's correct, but something that it will be useful later on. So let me write it like this. The preimage has the structure of a vector space. But moreover, like you said, so the preimage is exactly P at M. Okay, but it is important to note, this will be important later on, that the preimage is a vector space. Okay, so this is good. Now, of course, it's not any arbitrary vector space, it is the tangent plane at the point P. Now, also in this language, I would like to define some functions like this that go the other way around. From the manifold to the tangent space or the tangent bundle. And so it is a function, and this is like also one motivation of why Tm is important. In Euclidean space, you already saw vector fields. So in the language of the tangent bundle, a vector field is a very particular type of function from the manifold to the tangent bundle. So a function like this that goes to P comma V is what we used to call a vector field. Next week, we will cover vector fields on manifolds, but already what you know from Euclidean space, a function like this is precisely a vector field. And to be more precise, this is the condition that we require. So here is the same as this one. So vector fields are going to be functions from the manifold to the tangent bundle that satisfy this condition. Exactly this means that at each point you assign a vector that belongs to the tangent space at that point. So that's the relation that we use. Okay, so far this is just a sets. We start with a smooth manifold. We have a new space, Tm, a projection, and we have this special type of functions. So now we are going to give Tm a structure that it will make it a smooth manifold. But already note from the definition, if we assume that this is a manifold, what is the dimension of Tm? So P moves along the manifold. So let's assume that the manifold has dimension n. So here you have n parameters for the point P in the manifold. And now V moves in the tangent space to the point that has the same dimension as the manifold. Thus, this is going to have dimension twice the dimension of M. Okay? So let's move on and let's see this. So now we're going to give a smooth structure on Tm. The way that we're going to do this is by exhibiting an atlas on Tm. But the atlas on Tm that we're going to define will depend on an atlas of M. So every time that we have a smooth an atlas on the manifold M, we will be able to construct an atlas on Tm. So good. Consider a chart on the manifold M. Assume that P belongs to U. Then for any vector that you take, because we have an atlas, we can write it out locally like this. Right? If I take another chart that contains P, then I have a different description of the vector X. Okay then. Remember that if P moves in U, then the AIs are functions of the point. And they are smooth functions. Right? So this is something that we have been studying from a long time. I have U, I have my chart that goes to Euclidean space. I'm assuming that M has dimension n, and phi, in principle, phi is a homeomorphism to an open set. But later on, we show that in fact, phi is a diffeomorphism to the open set. Right, we have also the inverse function. and those functions are smooth. Okay. We are going to show that Tm, we're going to define a homeomorphism of some set in Tn. So remember that here I have this chart, and in terms of this, I'm going to define a new map. Now, first of all, we know what this is, right? Points in U and vectors tangent to the point. But remember that U is open, so having TUP is the same as TPM, okay? So I don't have any restriction on the tangent space, only on the point that only varies in U, not on all of N. So I define this function here, right? This is part of the chart, which is an open set in Rn. And the other Rn comes from the tangent space. So this is what I will call phi tilde. Is defined on Tu and is given by this. These are the coefficients of the vector which is written in the coordinates ddxi that are induced by the chart. Okay, now note that this map, when I put it like this map is a bijection. Okay, first of all, phi u, phi is a diffeomorphism between u and phi of u. That we know. And now this is any vector, so I have here the n parameters. So phi tilde is in fact a bijection. Onto some open set in Euclidean space. This is an open set in Rn square. Right? This is total space, and this is open by the definition of a chart. So I care about the tangent bundle Tm, and I managed to have a subset which is homeomorphic to an open set in Euclidean space. So again, I'm putting here the function that we have. This is exactly what I'm saying. So this is going to be my open set where I'm going to define a chart. And precisely this map is going to give me that information of a chart. Okay? Now, right, so before moving on, now I'm just going to make a few comments. They are written on the book in this part, but it is regardless to Tm. So far, Tm is only a set, and I have some subsets that they are very interesting in the sense that I have a map defined on them, which is a bijection onto some open set in Euclidean space. That's all I have. But now, the first thing that we need to do is to define a topology on Tn. And the topology that we're going to define on Tn is in the following manner. So remember, we started with a chart on M. And from a chart on M, we constructed this map. So we're going to say that the open sets in Tm are going to be precisely these sets and the image of any open set here under the inverse function. That's going to define me a topology on Tn. That topology will be Hausdorff. This is Hausdorff, is a subset of Euclidean space, and it will have all the conditions that are required for Tm to be a topological manifold. Okay? So that's how we define a topology on Tm. As U varies on the charts of M, Tu will be open set, and also the open sets here that will map to a preimage. That will also be open sets in Tu. And that's the topology on Tm. Now, note that it's not good only to have these sets as open sets, because Tu are very large, are very small in terms of M, but they have all of the vertical information, all the tangent space. So in that way, they are huge open sets. Okay, so this is what we have so far. This is what I was telling you. The open sets under the map are going to be open. Also, I would like to emphasize about this picture. I think it is very useful to get acquainted with tangent spaces. And also later, we will see tangent vector bundles. So remember, on the bottom, we will have the manifold. Above that, we will have the tangent bundle. We already defined the projection map here, pi. And above any point, you already responded to this, we have the tangent space at that point. Okay. Now, the other thing that we have about Tm is that it is locally Euclidean by using this. Remember that Tu is homeomorphic to some open set in Rn cross Rn. So Tm is already locally Euclidean. Right? So now I'm going to try to put this smooth structure on Tm. So far, if I take U's that cover M, the Tu's will cover Tm. So this is what we're going to see now. Tm has a manifold. And precisely we will show that if I have an atlas, the TUs will give me an atlas. That's what we're going to show in order to prove that Tm is a smooth manifold. Up to this point, any questions? Okay. Again, just remember that TU is an open set which is very large in Tm. So that's why this is good. We have more open sets, not only the TUs, but any open set here gives me an open subset in TU. Okay, so take an atlas. So we know that M is covered by all of the U's. Then we have this, right? Because I take here, any point in here is like this, P comma V. P is in the manifold. So P is going to be in one of the U alphas. So P comma V will be in that T U alpha. So if the U alphas cover M, T U alpha will cover Tm. We have this map that we defined before, which is a homeomorphism. So all that we need to show is that these charts are compatible, given by this. I have a cover of Tm by those open sets, and I would like to show that these charts are compatible. So in order to do that, let's only focus on M in the meantime, and then we will go to Tm. Right, so consider two charts, U and V, with coordinates x1 up to xn and y1 up to yn. And let's make a point in the intersection. And let's take a vector there. So I'm only considering points in the intersection of the open sets U and V. Now, all of this is happening on M so far. I'm not using Tm. So the vector can be written in two ways. In U, using the X looks like this, and in the Y entries, it will look like this. So these are some real numbers, okay? But let's see what is the relation between the A's and the B's. So basically, we need to, I will not show it here, I will tell you what it is, but we are just finding the matrix of change of bases. That's basically what we're doing, right? Because remember, that this is a basis as well as this one. So I'm writing a vector in terms of one basis and in terms of the other one. And then I have to compute the matrix, the change of basis matrix. So I claim that the A's can be recovered like this. Right? Because what I'm doing, I have an equality here. So I'm evaluating on both sides by the smooth function x1. Okay? Remember that you know very well the function xi are smooth functions. The same for the yi's. They are smooth functions. And you know how the differential acts on that. Hence, I evaluate the left-hand side on the function x1, and I only get this. On the right-hand side, I do the same, and this is exactly what I wrote here. And I do it for x2 and so on until xn. I get an on the left, and on the right, I get this. Now, for instance, if this vector moves in that same plane, so that means that the A's are going to vary, right? So the point P is fixed, but I let the vector x move. That means that the functions AI's change and also the functions BI's change. This is a smooth. Again, here is where the regularity condition is important. If xi is a ck function, then I will get a ck minus 1 function. because I'm taking one partial derivative. But the xi's are smooth functions. So this is a smooth, a smooth, a smooth. In other words, I can express the a's in terms of smooth functions like this. Everything is smooth. When you start to vary either the x in the same tangent plane, or if you move b and also x. What I'm saying is that the change of coordinates is smooth. Okay? Now, so when p varies and also when x varies. So I have smooth functions here. Okay, so all of this is only on M and what is happening on the overlap of two shards of M. But remember, we are aiming to show that Tn is a smooth manifold. We already have open sets, and now we would like to show that they are compatible when they intersect. So I have this drawing here. What I was explaining to you was happening only here on M, something that we know very well. So I want to have that T of U and T of V are compatible. So assume that U and V intersect. This is T of U, and this is T of V. Right? Know that the intersection of T of U and T of V is very large. Maybe U and V could be very small, but T of U intersected with T of V is something huge because you have Rn in that direction. Nice. Now, every time that I have the charts, so I didn't write it down. So like this. Every time that I have those charts, I got the new ones. The final TU, which is phi tilde U, and on TV, I have phi tilde V. Okay? And I want to show that these two charts are compatible. So this is the intersection. So I would like to show that we have a smooth map. Right? So it will be, has always, composed with, and this is the map that I would like to show that it is smooth. If we prove that, we have that the charts are compatible. Okay? From this to this, we know that that's going to be smooth because the shards U and V are compatible. So we only need to see what's going on here to here. And that's precisely what we did above. So this here is this, right? An open set in Euclidean space, an open set in Euclidean space. So this is this map. So let's show that that map is smooth. And I have the computations down here. Take any element here, I would call it Q, comma, the A's. And then here, I have phi U tilde inverse. It maps there, right? Now, basically I'm here, I just did this, now I have to go here. So for that, I apply phi of v to this, and then I just wrote the v's, but this should be understood in terms of this. So this is my smooth function. The transition function goes from here all the way up to here. So this function here. And we would like to show that that function is smooth. This entry only depends on Q, and it is smooth because U and V are compatible shards. Now, what about this entry? This one depends on the A's and on Q. And that's the relation that we have. I wrote the A's, but you can also write down the V's in a similar way. You will get dy over dxi. Okay, so this is smooth, this entry is smooth, and so on. Right? If you want to be a little bit more precise, V depends on Q and on the A's. Any V. And the way that it depends is given by this green box that I have here for the A's, but also works for the B's. Okay, so in this way, I have that these two shards that intersect and TM are compatible. They intersect here. this is precisely T of U intersection V. So in this way, what we have proved is that if I have an atlas of M, then this is going to be an atlas on Tm. That's it. Let me. So wait a second. Okay, sorry about that. So again, if I have an atlas of the manifold, I get an atlas of the tangent bundle. In that way, I get that Tm is a smooth manifold of dimension 2n. Okay. Are there any questions up to this point? Nice. Okay, so I will do some examples. More specific, what I want you to the whole idea of the examples is to get some feeling of what this looks like. First of all, so Tm is a manifold, and that manifold can never be compact because you have a vector space, plenty of them. So to speak, it goes to infinity, so to speak, right? So Tm is a smooth manifold that is not compact. I don't know if all of this, maybe you are saying that Tm looks like this. In some cases it does, in some cases it doesn't. Okay, and here by equal, I meant diffeomorphic to it. Later, I will give you some manifolds for which the tangent bundle looks exactly like this. So Tm is not necessarily M cross Rn, but locally it is. Locally it is. If I have a U that it is a short, then I know that Tu is the same as this one by using phi tilde. Okay? And however, when we find a diffeomorphism like this in this complex, something that it is very important is that the point P doesn't move that much. The phi tilde that we had before, remember here, it satisfies this diagram. Remember here, this was P comma V, and it was mapped to this, comma, A1, AN. This is the projection, so this will go to P, and here again the projection of the first entry. Okay, well, or even P if you want. They just take phi inverse of the projection. Okay, so basically, I want the point not to vary that much, only the vectors are allowed to move freely. But always, what I want is the tangent space go to another one. I don't want to mix the vectors. And what I'm saying here about this being a V field, oh wait, why is this diffeomorphism? Remember, if I have a chart, first of all, I know that this is a homeomorphism. And then we show that it is smooth, so this is a differential. We have seen this before. So every time that I have a chart, the function is a diffeomorphism. Now, what we proved before is that this is also a chart. Right? So that's why I'm saying that this is a diffeomorphism. Because we already proved that that's an atlas. So I have a chart, and that will be a diffeomorphism. Okay. Look, when we study manifolds, what we saw is that at a point, we have a small neighborhood that looks very much like an open set in Rn. If I have a manifold and I have a point, then there is a small neighborhood such that this one is an open ball, let's say. An open ball in Euclidean space. Okay? And a manifold is constructing by gluing all of these U's. And they are glued in a way that the transition functions are smooth. So that's a rough idea or a concept of a manifold. We are gluing open set of Euclidean space. We are putting it together to create the manifold. Now, on Tm, basically our canonical open set is precisely something like this. So the tangent bundle is constructed by gluing sets that look like this. Some open set in Euclidean space times Rn. So that's more or less how the way that we are constructing Tn, in analogy with the concept of a manifold here. Okay, so I'm going to give you examples. Most of the examples that we can do right now will give us a very trivial tangent bundle, nothing interesting, but nonetheless, they are important. So let's consider the manifold to be Euclidean space. So I have the tangent bundle of Rn. I'm going to define a map that is going to be a diffeomorphism. It is like this. So I take a point, a tangent vector, and I just send it to the same point and the coefficients of the vector. So define that map is a diffeomorphism. So the reason why this works is because on Euclidean space we have global coordinates. We have global coordinates, so I can define this. It is nothing different than what we have done before on the open sets of a chart. It is the same. But we know that Euclidean space admits a chart that covers the whole space. So I have a diffeomorphism. So if I have a manifold and I have a diffeomorphism such that the tangent bundle maps to this, making this diagram commute, I'm going to say that the tangent bundle is trivial. M has a trivial bundle if the tangent bundle of M looks like M times Rn. So I have a diffeomorphism from the tangent bundle to this. And so the tangent bundle basically looks like the Cartesian product. Rn has a trivial tangent bundle. And again, what I would like to show you, maybe not this class, but later, not every tangent bundle looks like this. That's not true. Okay. Again, I'm going to give you examples where this happens. We have Rn, and now let me give you the example of a Lie group. So consider a Lie group and take a basis of the tangent space at the identity. So you have n vectors there. Okay? Now, for any element of the group, we have this map right multiplication. Do you remember that this is a diffeomorphism? We saw that this is a diffeomorphism even the inverse is this map. Okay, so that map is a diffeomorphism. In particular, if I take the differential, that will give me a non-singular linear map. So I'm going to take the differential at the identity. Because this map is a linear isomorphism, I get that this is also a basis. It's a basis of now of that tangent space, right? I have a nonlinear map. So how would you define this diffeomorphism? So let's say this V, you can write it down. Sorry. This V, okay, so let's, is here, right? Then V, you can write it down like A1, and basically the same basis that you have on the identity, but now will be this one. So this makes sense? Right? Then, this is how you define this map. Like this. This map is a diffeomorphism. So the way that this works is basically a group. You can move to any point given 2 points in a group. In the meantime, forget any smooth structure whatsoever. If you have a group, you have here the identity element, but take any two other elements, G1 and G2. You can move from here to here. How? So you can multiply either the left or the right. So let's multiply on the right. Right? If you multiply G1 by this number, you get G2. So you can always do that on any group. Now, the fact that we have a link group, right multiplication and left multiplication are smooth maps. So whatever happens in one point, you have a diffeomorphism, either R or L, to move to any other point. And because it is a diffeomorphism, the local geometry, differential geometry on G1 is going to be the same as the local geometry on G2. So that's why this argument works. Here, we don't have global coordinates as Euclidean space. And you even know that from one example, the circle. The circle is a Lie group, but you don't have global coordinates on the circle. Otherwise, it would be R. But the circle and R are different. So on a Lie group, you don't have global coordinates, but you have a very natural way to move from one point to the other by a diffeomorphism. Using the multiplication that it is smooth because you are in a Lie group. So that's precisely what we are using to conclude that the tangent bundle of a Lie group is trivial. Any questions? For instance, something that you can see now, if G is the circle, so the tangent bundle of the circle is the cylinder. Let me draw it here instead. Here you have the projection map. So above a point, you identify this with the tangent space. And usually we write down here a line that represents R. And this R we need to think about it as a vector space. That's exactly what I asked you at the beginning. What is the pre-image of a point? Is a vector space. In this case, because the circle has dimension 1, the vector space is R. So this is the picture of the tangent space. It is better to work there than in R2. Here, for a point, this is the tangent line to that point. If you take this point, you have this. And the whole idea is of having the above picture than the lower one, just not to be confused with this vector and this vector. So it is better to think about it like the cylinder. Right? Now, the other thing that we cover is the map that goes like this. So the whole idea, at each point, you assign a vector. Okay? So far we have examples where the tangent bundle is trivial. That is for Lie groups and Euclidean space. Okay? The way that we show that Euclidean space is trivial was exploring what we learned at the beginning, that chart. But also remember that Rn is a Lie group. The operation means the sum of vectors. So that will give you another argument that this is trivial because Rn is a Lie group under addition. So more examples are like this. The sphere, I'm going to take only two-dimensional for the time being. The two-dimensional torus. Remember that this is S1 cross S1. So any torus is a Lie group. So this is trivial. For the sphere, this is not true. But so far, we don't have the tools to show you that.
How is the torus a Lie group?
Right, because so the torus, this is so the whole idea S1 is the unit vectors. So we have the product. complex product. Then for the torus, it's just the product of groups. Like this. Okay. So that's how the torus is a Lie group. Okay, so this is something that is not. Okay, now part that I want you to understand is precisely that not everything is trivial. There are a few cases when this happens, but it's not always the case. In order to show you something that is non-trivial in lower dimension in 2, I will do something more or less the same as the tangent bundle, but not the tangent bundle. And I will do it in 2 dimensions. Because what is the dimension of this?
Four, right?
Right. So if I want to consider tangent bundles of dimension 2, that means the manifold must have dimension 1. There are only 2 manifolds of dimension 1, the circle and the real line. Both of them have trivial tangent bundle because both of them are groups. So if I would like to show you something, a non-trivial tangent bundle, it must be at least dimension 4. So that's too big, but I would like to show you something related to a tangent bundle, but it is not a tangent bundle. So do you remember the Mobius strip? So I have to identify this side with that in that direction, right? And if you want, you can project here. So this will give me something like this. Right, so think of the Mobius strip that you can shrink it to the center, which is going to be a circle. Okay, now let's do this. Because if I make a point here, this is the projection. What is the pre-image of a point here? Under this projection. What can you say about the pre-image of this point? It's a closed interval, right? Okay. So in order that it will look like what we have done, if you want, let's omit the boundary. So assume that this is an open interval. In that way, the pre-image of a point is an open interval, and if you want, you can consider that R. Okay, now let's identify this line here. Okay? Assume that that's like at each point, the zero vector of the tangent space. Now consider any non-zero vector above this point, let's say. So that's a vector. And now, because basically this is R2, you can move it. Because what you want to do, you would like to do exactly the same that we did here. Like moving the vectors. Okay? So what happens if you move this vector to the left? Let's assume it is the same length. What happens when you reach all the way to the left, that you come from the right? You have it like this. And then you are here. What are you doing? You are moving the vector smoothly, right? And somehow here it appears that the movement wasn't smooth because you have opposite vectors. Basically, you have x and then minus x. But you were moving the vector smoothly. That means that the vector must vanish somewhere. Okay? You cannot have a non-zero vector everywhere. No, not blue, not purple circle. You cannot do that. So there must be a point eventually where this vector is zero. And after it's zero, it moves down. Down. You are here. And everything looks nice. So every time that you have a vector, it needs to vanish if you go all the way around. That's telling you that this space is not trivial. You cannot have this doesn't look like the circle cross an interval. That's not true because here you can do that. There on the circle you can take a vector, move it around smoothly, and you will reach the same point with no problem. The vector will never vanish. However, on the other side, you cannot do it. So here you cannot move a non-zero vector all the way around in this to vanish eventually, but here you can do it. So they cannot be the same. This is not a tangent bundle, but it is an example of a bundle, a vector bundle, that it is non-trivial. Also, note the following, something that we were working out also holds. If I take only one arc, let's say open, like this, this is U, this is a type of UV, V, and TV. But however, for the cylinder, we glue them like this. We don't do nothing. But to create the Mobius strip, we need to switch one. We need to create this turn in order to glue. But again, locally, this object is this and this. Looks very nice, trivial. But it is glued differently. For the cylinder, you just glue it like this. But for this one, you need to turn and then glue. And this type of spaces is the one that we were looking for, the tangent bundle. Trivial spaces, U cross R, V cross R. But they are glued differently to obtain different manifolds. So let's see if we can discuss a little bit why this is not true. Okay? So on the right-hand side, we have the same behavior that I told you about the cylinder. You can take a vector, move it around, non-zero vector everywhere, and there's no problem, right? Again, this is something that you can do also on the plane. You can take a vector, just translate it, and everywhere that vector will never vanish, right? So basically what I'm saying, and we will look this a little bit more. It's not the tangent bundle, so it's not a vector field, but basically you can create arrows along every point that never vanish, right? Now, I don't know if you have heard of what happens now on vector fields on the sphere.
The Hubble theorem.
Right. So now, and this one is for vector fields. If you have a vector field on the sphere, it needs to vanish at least in one point. In other words, the sphere does not admit a nowhere vanishing vector field. So in that case, this is actually a vector field on this side. And that's the argument that one uses to show this. So we have seen vector fields only on Euclidean space. Next week, we will see vector fields on manifolds. And we have seen the tangent bundle. But this result that you know for the sphere tells you that the spheres cannot be trivial. So know that if you have a manifold for which the tangent bundle looks like this, you can find a vector field that is nowhere vanishing. Okay? And in fact, you can do more, but at least with one vector field that is nowhere vanishing. Okay, so next time, the book, the next subject on the book is vector bundles. But I will prefer to do vector fields, and then we will do vector bundles. Vector bundles is just a straightforward generalization of the tangent bundle. This is an example of a vector bundle. It's not the tangent bundle of the circle. But then we will see vector fields now on manifolds. You know that on open set on Euclidean space. And we also discuss a little bit of vectors, vector fields on a chart when we were studying the differential. But now we will look at it on any smooth manifold. Are there any questions? Right, so just to wrap up, so we saw the tangent bundle. It is a huge manifold, twice the dimension of M. The tangent bundle comes with a canonical map to the manifold, which is the projection. Next time we will see a function that goes the other way around, and that's going to be our vector fields. Smooth functions from M to Tm. Great. So for today, we are done. So see you next week.
Professor, will we be having exam then next week?
Yes, but I think, so let's discuss. It will be like a homework, a take-home exam. So I will think about it. Maybe if I will, I don't know if I will give it to you this evening or on Monday, but nonetheless, you will have plenty of time to work it out. So we have a test. I have to report 3 grades. So we need to do the first one, and it will be next week.
All right. Thank you.
See ya.
Okay, see you. Bye.
See you next week.
Next week.